Hello students, welcome to Vyas Edification Kota. In this series of NCERT discussion, we'll continue further with Mathematics class 12th, and the chapter that we're dealing with is integrals. This is the 7th chapter of class 12th Mathematics, and now is the turn of miscellaneous exercise, the very long, interesting miscellaneous. Now in this, there are questions from throughout the chapter, all topics in the chapter. So first of all, there will be topics from indefinite integration, then there will be questions from definite integration, and we'll see all the questions one by one. Let's take a look at the first question. The question says, integrate the following functions 1 upon x minus x cube. 1 upon x minus x cube. How will we integrate that? So one of the ideas that comes to mind is that maybe you can use partial fraction by taking out x common. 1 minus x square will be 1 plus x 1 minus x. So that's one of the ideas, but then there's another idea that you can use over here, that is using substitution. You can integrate using substitution as well, and this is dx upon x minus x power 3. What you can do is, in the denominator, take out x power 3 common. Oh, this x will be reduced to 1 upon x square. This will be minus 1. And now use the substitution. 1 by x square minus 1 is equal to t. You see, the derivative of 1 by x square is minus 2 upon x power 3 dx, which is equal to dt. This is present over there. Yes. Therefore, I will be equal to integral dx upon x cube is minus 1 by 2 dt whole divided by 1 by x square minus 1, which is t. The integral will be minus 1 by 2 log modulus t plus constant. Or you can say that I will be minus 1 by 2 log modulus of t, log modulus of t. T is this 1 minus x square upon x square plus constant. At max you can take this minus in the power and you can take the reciprocal of this term, this, or half log of modulus x square upon 1 minus x square plus constant is what you'll get over here. This or this is the final answer for this particular question, as you can see over here. In the second question, we have 1 upon root of x plus a plus root of x plus b in the denominator. So what can we do over here? We can simply rationalize the denominator first of all and see where does that take me. So I is integral dx upon under root of x plus a plus under root of x plus b, and rationalizing the denominator, you multiply and divide with under root x plus a minus under root of x minus b. Numerator will be this. In the denominator you will have x plus a minus x plus b dx. What will this denominator simplify to? You see, x and x will get cancelled. What you'll get is 1 upon a minus b, and which will come outside the integral. Inside you'll have x plus a minus x plus b under root dx. And now under root of x plus a, this is x plus a power 1 by 2. The integral is very simple. Therefore, I will be 1 upon a minus b outside. X plus a power 1 by 2, the integral will be x plus a power 3 by 2 over 3 by 2 minus under root of x plus b, that is x plus b power 1 by 2, the integral will be x plus b power 3 by 2 upon 3 by 2 in brackets plus constant of integration. This is what you'll get. Okay, so 1 upon a minus b is okay. And what else? You have a 2 by 3 coming out common from here. And in the bracket you have x plus a power 3 by 2 minus x plus b power 3 by 2 plus a constant of integration. That is my required answer for this question, as you can see over here. In the third question, we have 1 upon x under root of ax minus x square. And there's a hint also given over there, put x equal to a by t. How do we attempt this? So we can directly put the substitution, yes. But why do we put this substitution? Why do we use this substitution is something that we should be aware of. So x under root of ax minus x square is what I have. So I need to create something over here such that this outside term along with dx becomes the derivative of this term over here. So the simple idea that you can apply is take this x square common from the under root. X square under root will be x. There's an x already outside, so this becomes x into x, which is x square. Under root of, if you take out x common, this is a by x, and this is 1 over here. Yes. And now you can observe that this a by x can be substituted as t, or you can substitute x as a by t. Alternatively, you can also think of putting a by x minus 1, this whole expression, as t, or for that matter, you can also substitute this as t square. Oh, we are not using this? No, we are using something better than this after reaching this stage. So a by x minus 1 can be substituted as t square. 1 upon x, the integral derivative will be minus a by x square dx, which is 2t times dt. This is what I have, right? Therefore, the integral will be equal to what? Dx upon x square is 2t upon minus a dt upon, what is this? Under root of a by x minus 1, which is t. This is what I get. So this overall is minus 2 by a comes outside. Integral of t upon t is 1. dt is what I get. And therefore, I is equal to minus 2 by a times integral 1, which is t plus constant, or minus 2 by a times t. T is under root of this whole expression plus constant. This, or you can further simplify it as, you can write it as under root of a minus x upon under root of x plus constant. This is this, or this is the final form of the answer that you may require, right? That's the final solution, complete solution of this question. In the fourth question, we have 1 upon x square times x power 4 plus 1 whole power 3 by 4. How will we handle this? So we have 1 upon this, I is equal to integral dx upon x square times x power 4 plus 1 raised to power 3 by 4. Okay. If you see x power 4 power 3 by 4, that x power 4 can come out common, and this will be reduced to dx upon x power 4 power 3 by 4. What is that? X power 3. There is x square outside, this becomes x power 5. What remains is this inside. And now I can use substitution. 1 plus 1 upon x power 4 is equal to t. The derivative of this is present outside with dx. So this tells me minus 4 upon x power 5 is this, the derivative dx is equal to dt, right? This is the differentiation of this. Dx upon x power 5 is minus 1 by 4 dt. And what's there in the denominator? You have 1 plus 1 upon x power 4, which is t power 3 by 4. This is what you get, right? So the integral will be minus 1 by 4 is okay. T power minus 3 by 4, the integral will be t power minus 3 by 4 plus 1 upon minus 3 by 4 plus 1 plus a constant. What is that? This is 1 by 4. This goes with this 1 by 4. This is 1 by 4. So this is minus t raised to power 1 by 4 plus constant. What is that? Minus is okay. T is this expression. So this is x power 4 plus 1 upon power 1 by 4 plus constant, which can further be written as, please observe, x power 4 in the denominator raised to power 1 by 4 will give me an x. So minus of x power 4 plus 1 raised to power 1 by 4 upon x plus constant is what I get. That is my required answer for this question, as you can see over here. In the fifth question, we are given 1 upon x power 1 by 2 plus x power 1 by 3, and there's some kind of a hint also given over there. So let's see, the steps involved are pretty interesting and they are already mentioned over here. So once I can write this as this, what do I have? I have x power 1 by 3, 1 plus x power 1 by 6, this, okay. And now this power 1 by 6 is actually the issue. So to handle that power 1 by 6, we can simply put x equals t power 6 as is mentioned, dx becomes 6t power 5 dt. And this tells me I will be equal to what? I will be integral of dx, which is 6t power 5 dt upon x power 1 by 3. X power 1 by 3 will be t power 6 power 1 by 3 t square. 1 plus this x power 1 by 6 will be t. This is what you will get, right? That 6 can come outside the integral. In the integral you have t power 3 upon t plus 1 dt. And now this is the integral that we are looking to find. So t power 3 upon t plus 1, this is a polynomial. This is also a polynomial of higher degree and lower degree. So first we'll divide this, right? T cube will have a factor over here. I can add a 1 and I can subtract a 1. This is the important step, right? If I add a 1, t cube plus 1 will be easily divided with this, because t cube plus 1 has one factor, t plus 1. The other factor, t square minus t plus 1, right? Pretty simple, yes. So 6 is okay. Integral, this will be t square minus t plus 1 over here. That's the first part. And then you have minus 1 upon t plus 1. That's the second part of this whole expression dt. After this, I can have I will be equal to what? Now you can simply integrate this. In the bracket, t square integral will be t power 3 by 3 minus t square by 2 plus the integral of 1 will be t minus log modulus 1 plus t bracket close plus constant of integration. This is what you have. Right. So 6 by 3 is 2. T power 3. What is t power 3? It is under root of x, which is x power 1 by 2. Plus 6 by 2. Sorry, there's a minus over here, not a plus. So this is minus t 3 times t square. T square is x power 1 by 3. Plus 6 t. T is x power 1 by 6. Minus log. There's a 6 also coming inside. Minus 6 log modulus of 1 plus, let's write this 1 plus, minus 6 log modulus of 1 plus t. T is x power 1 by 6 plus constant of integration. That is my required answer for this question. As you can see, the steps over here. In the sixth question, we have 5x upon x plus 1 x square plus 9. Now this is, in the denominator you have two linear and quadratic factors. So yes, we'll be using partial fractions over here. 5x upon x plus 1 x square plus 9 is equal to a upon x plus 1 plus bx plus c upon x square plus 9. This is the form of partial fraction that we need. The value of a can be found easily by multiplying with x plus 1 throughout and putting x equal to minus 1. This will become 0. This will become minus 5 upon minus 1 square, which is 1, plus 9 is 10. That tells me a will be minus 1 by 2. You can find b and c as well by comparing the numerators. So 5x is equal to a times x square plus 9 plus bx plus c. Taking the LCM in the numerator, you will get this, right? And from here, what do I observe? Ax square bx square, that is the coefficient of x square on the right hand side, which is equal to 0 on the left hand side. So there is no term of x square over here. And since a is equal to minus 1 by 2, b can be found over here. What else? Constant term, sorry, coefficient of x, bx, cx. So b plus c is the coefficient of x, which is equal to 5 over here. And 9a plus c is equal to constant term, which is 0 over here. So if you know a, from here you can easily get b is equal to 1 by 2. And you can easily get c will be minus 9a, which is 9 by 2. And yes, for these values, this is also true. That's what you can verify easily. So once you have found a, b and c, now I can take a look at the integral of this whole expression. I will be integral of that, which is integral of this. A upon x plus 1 is minus 1 by 2 upon x plus 1 plus. bx plus c, 1 by 2 plus 9 by 2, 1 by 2 x plus 9 by 2. So this is x plus 9 by 2 times x square plus 9 is what I get, dx. 1 by 2 plus 9 by 2. Let's write that 9 properly. This is 9, right? Okay, what else? So this can be integrated easily, but for integrating this expression over here, x square plus 9 with 9 is easy. You have to create derivative of x square plus 9, that is 2x over here. Okay, so let's write it in that particular form. Minus 1 by 2 integral dx upon x plus 1 is okay. That's simple. X square plus 9, the derivative is 2x, so there should be a 2 over here first of all. Okay, so we multiply with a 2 and divide by 2. This becomes a 4. 1 by 4 integral 2x upon x square plus 9 dx. And the last term is 9 by 2 integral dx upon x square plus 9. This can be handled directly. This is x square plus a square in the denominator, whose integral will be 1 by a tan inverse x by a. Yes. What is this equal to? This is 1 by 2 minus log modulus x plus 1. What is this? Plus 1 by 4. If this is t, then 2x dx will be dt. So this is dt upon t, which will be log modulus x square plus 9. Since x square plus 9 is always positive, we can write it as this as well, right? Without writing the modulus as such. And 9 by 2 is okay. Dx upon x square plus 3 square is 1 by 3 first of all. So 9 by 2 into 1 by 3, this is 3 by 2. Tan inverse x by a plus a constant, and that is my required answer. Let me get aside for you to take a look at this complete solution over here. That's all in this question. First use partial fraction and then you integrate, right? Question number 7th, we have sin x upon sin x minus a. Now this sin x minus a is creating a problem. Had these been at the top, we will directly expand sin x minus a, but then if we do not have this on the top, can you create sin x minus a on the top? Yes. Sin x can be done as x minus a plus a. And in the denominator, you have sin of x minus a dx. Now, if you observe, this is one angle, this is the other angle, right? Take a look at this as sin first angle plus second angle, okay? And we can expand that. Sin first angle cos second angle plus cos first angle sin second angle. Sin x minus a remains as it is in the denominator. And what will this simplify into? Now you can divide. Sin x minus a will be simplified. Cos a is what remains from here. What remains is cos a plus cos x minus a sin a upon this is cot of x minus a times sin a. This is what remains, dx. Okay. What else? What about the integral of this? So cos a is a constant, mind you. So integral I will be equal to cos a, which is a constant, comes out, times integral of dx, which is x, plus sin a is a constant, comes out, and cot of x minus a, the integral will be log modulus sin of x minus a, dividing by the coefficient of x, which is 1, is irrelevant over here. Dividing by 1 will also give me this only. So the final answer will be x times cos a. Let me write that properly. X times cos a plus sin a times this whole expression. And yes, that's the required answer for this question over here. This is the 7th question for us. In the 8th question, we have a very complicated looking expression. But if you observe this carefully, this is e power 5 log x. Okay. This x and e can interchange their positions, yes. E power 5 log x. This e can go over here, this x can come over here. This will be using properties of log. X power 5. This is x power 5 log e. And what's the base of this log? This log base is also e. So therefore this becomes x power 5. Log e base e is nothing but 1, right? So this becomes x power 5 only, yes. So similarly, you can check all the other terms. This is actually integral of x power 5 minus x power 4 upon x power 3 minus x power 2 dx. This is what you have. That is the integral that we are looking to solve. I can take out x power 4 common from here. What is remaining is x minus 1. I can take out x square common, and what remains is this. Oh, that looks simple now. So on simplification, you are only left with x square dx, and the integral will be nothing but x cubed by 3 plus constant. Yes, that's all that you have in this question. That's the final answer for this 8th question. In the 9th question, we have cos x upon 4 minus sin square x, and you can clearly observe that the derivative of sin x is present at the top. So dx, just a minute, this is cos x, not dx. I equals cos x upon under root of 4 minus sin square x dx. This is what you have. Cos x upon under root of 4 minus sin square x dx, and let sin x is equal to t. That's the substitution that will make. If sin x equal to t, that implies cos x dx will be equal to dt, and therefore integral I will be equal to what? The numerator will have cos x dx, which is actually equal to dt upon under root of 4 minus sin square, which is t square. This is what you have. And you see dt upon a square minus x square type of expression. The integral will be sin inverse x by a plus constant, or you can write it as further sin inverse t. T will be replaced with sin x by 2 plus constant. That is my required answer for this question, as you can see over here. In the 10th question, we have sin power 8. Okay, there should be a x over there. Sin power 8x minus cos power 8x upon 1 minus 2 sin square x cos square x. How will we handle this? So there's a new complicated expression in the numerator as well as denominator. But can you simplify the numerator first? Denominator, we'll take a look at the denominator. This is square of sin power 4. This is also square of cos power 4. So this is nothing but sin power 4 square minus cos power 4 square. A square minus b square can be written as a plus b, a minus b. So I can write this as sin power 4 x plus cos power 4 x, and this as sin power 4 x minus cos power 4 x. These will be the two terms, right? In the denominator, you have 1 minus 2 sin square x cos square x dx. Okay. Now sin power 4 plus cos power 4, this can be converted into perfect square, because this is nothing but square of sin square. This is nothing but square of cos square, and we know that a square plus b square can be written as a plus b whole square minus 2ab. Use this. A square is sin power 4, therefore a is sin square, right? We are taking a as sin square, so this becomes integral of sin square x plus cos square x a plus b whole square minus 2 times ab, in this manner, into cos square x. This is what you have. Okay, this is one of the terms. This other term, what does this simplify into? So this is again sin square square minus cos square square, which can be written as plus cos square x sin square x minus cos square x. Yes. And in the denominator, we have this 1 minus 2 sin square x cos square x with dx. Now, what next? Sin square x plus cos square x is equal to 1, right? So this will be 1. 1 square will be 1. 1 minus 2 sin square x cos square x. Oh, this and this will get cancelled. Yes. Sin square x plus cos square x will be 1. This is 1. So what we are remaining with is this. But we know that cos 2x is equal to cos square x minus sin square x. So this is nothing but minus of cos 2x, negative of this. Yes. Oh, The whole expression basically simplifies to minus of cos 2x. Yes, that's what I mean to say. Integral of minus cos 2x dx is what you're looking forward to. And what's the integral of cos 2x? That's simple, sine 2x by 2. That is my required answer for this question. So the complicated thing in this question is trigonometric simplification. Rest everything is simple. After that, the calculations become very simple. Integration is not at all difficult in this. That's all that you have in this 10th question. For 11th question, we have a very familiar expression, 1 upon cos x plus a, cos x plus b, right? So both the terms are of cos. What we'll do is, we'll multiply and divide with sine or cos. So sine has sine and cos both, right? So we'll multiply and divide with sine of the difference of these two angles. Right. So difference of these two angles, x plus a minus x plus b of sine minus x plus b. What is this? X minus x goes, a minus b is what you get. Multiply with this and divide with this. Sine a minus b is what you have. Okay, and then you have cos of x plus a and cos of x plus b as well. This is what you are doing. For integration, this is the first step that you have done. So you have multiplied with this and, you have multiplied with this and divided with the same terms, right? Okay. And now I'll expand this sine of capital A minus capital B types expression. So integral 1 upon sine a minus b remains as it is. We can take the integral, we can take it outside the integral. Yes, yes. So let's take it outside the integral. Inside the integral, you have sine this, cos this. Okay. Minus cos x plus a sine x plus b. And now you will see the benefit of applying that step. Cos x plus a times cos x plus b is what we have in the denominator. Dx is already there, right? So this cos x plus b, this cos x plus b will get cancelled from the first term. Yes, 1 upon sine b minus a remains as it is. Integral this term upon this, cos x plus b gets cancelled, sin x plus a, cos x plus a will be tan x plus a, minus this upon this, cos x plus a gets cancelled, sin upon cos is tan x plus b, and that's what you get with dx. This is okay, yes. And integral of tan is very simple. We'll directly integrate that. This is 1 upon sine b minus a times tan of something. The integral is ln mod sec x. So ln mod sec x plus a is what you are getting over here, minus ln mod sec x plus b is what you are getting over here in large brackets, plus constant. At max you can, this is final answer, at max you can merge these two logs. This is okay. For NCERT we generally do not prefer ln form, we prefer writing log, right? Log of mod sec x plus a, log of mod sec x plus b, log of x minus log of y can be done as log x upon y as well, and that is my answer for this question. Or the other form that I just mentioned, 1 upon sine b minus a remains as it is. You get log modulus sec x plus a upon sec x plus b plus constant. This or this form, both are correct. This is the 11th question for us. In the 12th question, we have x power 3 upon under root of 1 minus x power 8. Now x power 8 is nothing but square of x power 4, right? So we can simply use substitution over here. This is x power 4 square dx, right? So we can put x power 4 is equal to t. What does that give me? 4 x power 3 dx is equal to dt. This is what you get. 4 x power 3 dx is equal to dt. Therefore, I is equal to integral of x power 3 dx is 1 by 4 dt upon under root of 1 minus x power 4 square, which is t square over here. This is what you have, right? Yes. And what is this equal to? This integral is not difficult. 1 by 4 is okay. This is a square minus x square. Sine inverse x is what I'll get. Sine inverse t plus constant. What is that? 1 by 4 sine inverse t. T is nothing but x power 4 plus constant. That is my required answer for this question, as you can see over here. In the 13th question, we have e power x upon 1 plus e power x 2 plus e power x. So the first thing that I can see is that this e power x derivative is present over there. Yes, that's the first thing that you can observe. I is equal to integral of e power x upon 1 plus e power x 2 plus e power x dx. So we can substitute e power x as t, or to be more pragmatic, why not put 1 plus e power x as t? That tells me e power x dx will be equal to dt, and just adding this one will simplify this expression to simple t. dt upon t, 1 plus e power x is 1 plus t. And now writing as partial fractions is very easy, right? This can be done as integral 1 plus t minus t. What is this? This is simply 1, right? T times 1 plus t. Oh, what about partial fractions? Those a upon t, b upon 1 plus t. We're not using that. We can directly handle this one, right? 1 plus t. The first term will be 1 by t. The second term will be minus 1 upon 1 plus t. So this 1 plus t upon this whole will be 1 by t minus 1 upon 1 plus t. Just a bit pragmatic. This is what you have. So 1 upon t, the integral will be log modulus t minus log modulus 1 plus t for the other term plus constant. And we can merge these two logs. Yes, we can merge these two logs. So this will be log modulus t upon 1 plus t plus constant. What about the value of t? T is 1 plus e power x. So this will be log modulus 1 plus e power x upon 1 plus 1, which is 2 plus e power x modulus. This is my final answer for this 13th question, as you can see over here. In the 14th question, we have 1 upon x square plus 1, x square plus 4. Okay, this can again be manipulated to break into two parts, which we can easily integrate. X square plus 1, x square plus 4 dx is what I have, and the difference of these two is a constant. Yes, see that? So x square plus 4 minus x square plus 1. I'm taking the difference. What have I done over here? I have simply multiplied with, you can say 4 minus 1, 3. So if I have multiplied by 3, let's divide by 3. Yes, that is okay. Yes, and once I do that, this becomes integral of 1 upon x square plus 1. This becomes 1 upon x square plus 4. After separating the two terms, this is what you get. Okay, that's simple. And 1 by 3 is okay. 1 upon x square plus 1, the integral is tan inverse x minus this x square plus a square. The integral will be 1 upon a tan inverse x by a. A is 2 plus constant. This is what you get. Or you can write it as 1 by 3 tan inverse x minus 1 by 6, multiply this, tan inverse x by 2 plus constant. That is my required answer for this 14th question, as you can see over here. In the 15th question, we have cos cube x e power log sin x. Once you have that e power this, can you see that we can take this in the power and this over here by applying properties of log. This will be sin x power log e, which is sin x only. So I'll write that expression now. This here, I is actually cos power 3x times sin x. Integral this dx, simple this. And integration of this is not difficult. Cos x, derivative is sin x. So we can put cos x is equal to t. That tells me minus sin x dx will be equal to dt. Okay, once you do that, I will be minus dt cos power 3, which is t power 3. This is what you'll get after substituting this. This is what you'll get, minus this is t power 4 upon 4 plus constant. Yes, and what is the value of t? T is cos x. So this is minus 1 by 4 cos power 4 x plus constant. That is my answer for this question over here. In the 16th question, we have e power 3 log x, which will again simplify to by simple taking this over there and this over here, x power 3. So what do I have? I is equal to integral of x power 3 1 upon x power 4 plus 1 dx, and the derivative of this is present over here. Yes, x power 4 plus 1, the derivative is 4x cube. Let's multiply with the 4, let's divide with the 4. This becomes 1 by 4 dt upon t. The integral will be log modulus x power 4 plus 1, and since this is positive, there is no need of modulus as well. That is my required answer for this question. Very simple, yes. In the 17th question, we have f prime ax plus b and f of ax plus b power n, and if you note, I can substitute f of ax plus b is equal to t. What I'll get is f prime ax plus b times a dx is equal to dt. Therefore, the integral will be equal to what? F prime ax plus b dx will be 1 by a dt. F of ax plus b is t, this will be t power n. And the integral will be t power n plus 1 upon n plus 1 plus a constant. Although a condition should have been given that n is not equal to minus 1. Had n been equal to minus 1, so you can write another result over here. Had n been equal to minus 1, then this would have gone to this direction, log modulus t plus c. Okay, if n equal to minus 1. Otherwise, this is the answer that we're looking forward to, right? So you know both the answers. At the end, simply substitute the value of t. This is t. T is f of ax plus b power n plus 1 upon a times n plus 1 plus a constant. That is my required answer, or this one, right? You can see this carefully, right? That's the final answer for this 17th question. In the 18th question, we have 1 upon sine cube x sine x plus alpha. How will we handle this? So in the under root, in the denominator, if you have sine cube x and sine x plus alpha, that's not something good. But if you observe this carefully, this sine cube x, okay, this sine x plus alpha will have another sine x, right? Sine x cos alpha, cos x sine alpha, yes. So I can take out another sine x from here, this becomes sine power 4x, and I can take that out from here. So integral of sine power 4x under root is actually sine square x in the denominator. In the numerator, it will become cosec square x. And what is remaining here is sine x plus alpha, and you took an extra sine x from here. Let's give that back, right? So I've taken sine power 4 common, which becomes this, and what is remaining is this in the denominator. Now, let us use expansion of this. The benefit of doing this will be visible evidently. Sin x cos alpha, this sin x goes, so this becomes cos alpha plus cos x sin alpha, cos x upon sin x is cot x sin alpha. And now do you see the beauty of this step? That in the denominator you have a complicated expression, but its derivative is present in the numerator. Don't worry about cos alpha and sin alpha, these are just constants. Worry about only this cot x, which is the problem. So put cos alpha plus cot x sin alpha as t. This is what you can do, yes. And the derivative will be minus cosec square x times sin alpha, which is a constant, dx is equal to dt. Therefore, I will be equal to cosec square x dx will be minus 1 upon sin alpha dt under root of this whole expression, which is t. Oh, 1 upon root t. This is t power minus 1 by 2. The integral will be t power 1 by 2 upon 1 by 2, which is 2 root t. 2 square root of t plus constant. And minus 1 upon sine alpha is okay. This is 2 square root of t is square root of this. Cos alpha plus cot x sine alpha plus constant. Either you can leave the answer at this stage, or you can go back to that particular form of sin x plus alpha, because this cot x is cos x upon sin x cos alpha, cos x sin alpha. In the numerator you will have sin x plus alpha, in the denominator you will have sin x under root. So minus 2 upon sin alpha under root of sin x plus alpha upon sin x is what you will get over here. This or this plus c is my final answer for this question, as you can see over here, with this complete solution. In the 19th question, we have something interesting, very interesting. What do we have? Sin inverse root x minus cos inverse root x. How will we handle this? In the denominator, you have sin inverse root x plus cos inverse root x. That is simple, right? This denominator is equal to pi by 2. Yes. So I is equal to, in the denominator, if you have pi by 2, do you see that this sin inverse root x, I can also write it as pi by 2 minus cos inverse root x. Yes. So this becomes pi by 2 minus cos inverse root x minus another cos inverse root x will be this dx. This is what we are looking to integrate. Yes. Okay, let's divide these to 1 minus 2 upon pi by 2 is 4 upon pi cos inverse root x dx. So 1 is easy, 4 by pi is not an issue. We are interested in this cos inverse root x, this integral. So let's try to find this integral somehow. Let's focus on I1. If you can find this, then life would be very easy, right? Okay, you'll be able to get I very easily after that. So this is cos inverse root x. One of the ideas is to apply by parts directly by taking first function as this, second function as 1, right? Or another idea could be to use substitution first. So let's use substitution. Cos inverse root x is equal to t. What does that tell me? Put this. Root x is equal to cos t. Okay, and x equal to cos square t. What about dx? Dx will be equal to 2 cos t into minus sin t dt, which becomes minus of sin 2t. 2 cos t sin t is this dt. This is what you get. Okay, therefore this I1 becomes equal to what? Integral of cos inverse root x, which is t. Dx is minus sin 2t, there is a minus sin 2t dt. And now I can apply by parts on this. After making this substitution, now I can apply by parts. There is an algebraic function, a trigonometric function. This will be taken as the first function u. This will be taken as the second function v. This is what you will do. So therefore I1 will be equal to minus 1, that comes out common. In the bracket you will have first function times integral of second function minus cos 2t upon 2. That's the integral of the second function minus integral of derivative of t, which is 1. Integral is minus cos 2t upon 2 dt in the square bracket. What does this give me? So this is not difficult. Minus minus becomes plus t by 2 cos 2t. And this minus becomes a plus, but with this minus it becomes a minus again. The integral of cos 2t is sin 2t upon 2 plus a constant of integration. This is what you get. Is that okay? Yes. Okay. And what about these cos 2t and sin 2t? We have cos t as root x. So I can write cos 2t and sin 2t in terms of this cos t and then substitute it as root x, right? Okay. So this I1 will be equal to t by 2. T is cos inverse root x. 1 by 2 cos inverse root x times cos 2t. Cos 2t is 2 cos square t minus 1. 2 cos square t, which is 2 under root of x square, 2x minus 1. Minus 1 by 4 is okay. Sin 2t is 2 sin t cos t. Okay. Cos t is this, 2 root x. Sin t will be under root of 1 minus cos square t, which is under root of 1 minus x. This is what you get, plus a constant. So we have almost simplified this. This is, have we taken care of that minus? Yes. This is 2x minus 1 by 2 cos inverse root x. And this is minus 1 by 2 root of x minus x square plus constant. But is this the final answer? No, this is just the value of I, 1. Let's write the value of I. Therefore, I will be integral of 1 is x minus 4 by pi. I1 is what we are looking forward to. I1 is this, 2x minus 1 by 2 cos inverse root x minus 1 by 2 root of x minus x square, and multiply this with this, make this c prime or c1 for that matter. That's the constant of integration, new constant of integration over here. This is my final answer for this question, as you can see over here. At max we can multiply with this 4 by pi inside and we will get a slightly different form, but this is the final solution and the final answer for this question. In 20th question we have 1 minus root x upon 1 plus root x in the under root. Okay, how will we handle this? So this question can be handled. One of the ideas is to rationalize this. Another idea is to use substitution initially, and that will make things very simple. You see 1 minus something, 1 plus something, exact same thing. So this is 1 minus cos 2 theta upon 1 plus cos 2 theta form. This under root also, that also gives us the idea. But you have 1 minus root x upon 1 plus root x under root dx, and we put root x is equal to cos 2 theta. The benefit of this is 1 minus cos 2 theta, 1 plus cos 2 theta is nothing but tan square theta. Under root will make it tan theta, simply tan theta. Yes. X here will be cos square 2 theta, and the derivative dx will be 2 cos 2 theta minus sine 2 theta d theta. This is what you'll have. Is that okay? Yes. Therefore, I integral, this becomes under root of tan square theta, which is tan theta. What are we using over here? Using 1 minus cos 2 theta. This simplifies to 2 sin square theta. This simplifies to 2 cos square theta. This is tan square theta. You should remember this from your concepts of trigonometric functions. This is tan theta. Dx is 2 cos 2 theta. Sin 2 theta, which is with a minus, this is what you get. Now, how do we solve this? So, in sin 2 theta, what do I have? I have 2 sin theta cos theta, 1 cos theta from here and 1 cos theta from here, denominator will get cancelled, yes. So, that will simplify our expression a bit. Therefore, I is equal to 2 sin theta cos theta, 2 will come out. This becomes a minus 4 integral. Tan theta will be sin theta upon cos theta. This will be 2 sin theta cos theta. That becomes a sin square theta into cos 2 theta d theta. Now this integration has to be made simpler. How will we make that? This cos 2 theta is pretty simple. Sin square theta has to be converted into the form of cos 2 theta first. Okay, and this is 1 minus cos 2 theta by 2. So this becomes minus 2, 1 minus cos 2 theta times cos 2 theta d theta. Now this becomes quite simple, not simple enough. This is cos 2 theta minus cos square 2 theta. Now cos square 2 theta is 1 plus cos 4 theta by 2. And now this integrand has been converted into form which can be integrated, which gives me I will be equal to what? This I will be equal to minus 2 remains as it is. In the bracket you have cos 2 theta. The integral of cos 2 theta will be sin 2 theta by 2. You have minus 1 by 2, which is theta by 2. Minus 1 by 2 as well. Cos 4 theta, the integral will be sine 4 theta by 4. Bracket closed, plus a constant of integration will be introduced over here. What is this? Minus 2 by minus 2, this is minus sine 2 theta. Minus 2 by minus 2, this is plus theta. Minus 2 by minus 2, this is plus 1 by 4 sine 4 theta plus constant. But now we need to replace theta in terms of x. Okay. How will we do that? So we observe a lot of things over here. Cos 2 theta is root x. Sine 2 theta will be equal to, sine 2 theta will be simply under root of 1 minus cos square theta 2 theta. So under root of 1 minus under root x square, which is x, this is what you'll get, plus theta. Theta is cos inverse root x divided by 2 plus 1 by 4 sine 4 theta can be handled with cos 2 theta and sine 2 theta. This is sine 2 theta, that is cos 2 theta. This is nothing but 2 sine 2 theta cos 2 theta, which is root x plus constant. This is what you have. Is that okay? Yes. That looks okay. This is minus square root of 1 minus x plus half cos inverse root x plus 1 by 2 root of x minus x square plus constant over here. That is my complete solution, and the final answer for this question, as you can see over here, using these few steps. And let us check the calculations once again. We missed out on one theta. Where is that theta? Where is that theta? Sorry, not theta. Actually, this dx will be 2 cos 2 theta sine 2 theta and a 2 d theta. Okay, this will be a 2 d theta. So this becomes twice. Oh, we missed out on that 2. Therefore, there will be a 2 over here. There will be a 2 over here. There will be a 2 over here. And yes, there will be a 2 in product over here. There will be extra 2. So this is extra 2. And yes, there will be extra 2 over here. This will be 2. This will be 2 upon 4. Oh, bad. But we missed out on that 2. That idiotic 2. But never mind. Now we can make this. And this becomes this. This is again 2 by 4. And now small modification in the answer. This is minus 2. This is 2 by 2, which gets cancelled. Yes. And what else? This is also 2 by 2. This also gets cancelled. Yes. And that here will be the final answer for this question number 20th, as you can see over here. In 21st question, we have e power x 2 plus 2 sin x, 2 plus sin 2x upon 1 plus cos 2x. Now this is, along with e power x, we have some things, right? Okay. And when we see e power x, we try to convert it into a special integral, that is e power x times fx plus f prime x, if we can. Since they are trigonometric functions, either we'll be applying by parts or that special integral which is obtained from by parts only. I is equal to integral of e power x times, what do I have? This is 2 plus sin 2x is 2 sin x cos x. And I can write 1 plus cos 2x as 2 cos square x. Oh, 2 comes out common, 2 comes out common, and 2 actually gets cancelled. This is 1 only. Yes. So this is integral e power x 1 upon cos square x, which is nothing but sec square x, plus sin x cos x cos x cos x, which is tan x dx. Very interesting. So if this is function, then this is nothing but the derivative of function. So e power x fx plus f prime x is the form that we get, and the final answer will be e power x fx plus constant. That is my required answer. Very simple. Yes, that's the final answer for this 21st question. In question number 22, what do we have? X square plus x plus 1 upon this whole expression. Yes. How will we handle this? So the first thing that we'll do is, obviously the denominator has been factorized into linear factors. The degree of numerator is less than the degree of denominator, so we'll use partial fractions. So let's convert x square plus x plus 1 upon x plus 1 square times x plus 2 into a upon x plus 1 b upon x plus 1 square c upon x plus 2 in this form. Let's convert this into this form. Once we do that, can we find the values of a, b and c? What is a equal to? Oh, a will be difficult, but b can be found directly. We can multiply with x plus 1 whole square, and this term, put x equal to minus 1, this will become 0, this will become 0. Put x equal to minus 1, this will be 1 minus 1 plus 1 upon x plus 2, which is minus 1 plus 2. This is 1 upon 1, which is 1. So that gives me b is equal to 1. What about c? C can also be found directly by multiplying throughout with x plus 2 and putting x equal to 2. So this becomes 0, this goes away. Putting x equal to minus 2, this becomes 4 minus 2 plus 1. What is that? 3 upon 1, which gives me, okay, this gives me c equals 3. Is that okay? Yes. What about the value of a? A can be found by comparing the numerators. That is x square plus x plus 1 is equal to a times x plus 1, x plus 2. And this is what we have, yes. And what do we have? Plus b times x plus 2 plus c times x plus 1 square. So you can compare coefficients of x square, which is a plus c, which is equal to 1. A plus c is equal to 1 implies a will be equal to 1 minus c, which is minus 2. This is what you will get. Yes. So b, c and a have been found. You can find a, b and c by comparing the coefficients and this as well directly. But once we find a, b and c, therefore I will be integral of this expression, or basically this expression, a upon x plus 1. This, yes. This is okay? Yeah, this is okay. What else? B upon x plus 1 whole square, this, which is 1 upon x plus 1 whole square. And C, which is 3 upon x plus 2 integral dx. What is this? This is minus 2 log modulus x plus 1. 1 upon x square, the integral will be minus 1 upon x. Okay. Plus 3 times log modulus x plus 2 plus constant, and that is my required answer for this 22nd question, as you can see over here. Question number 23 says integrate tan inverse root of 1 minus x upon 1 plus x. Now the moment I see that 1 minus x upon 1 plus x in under root, I feel like substituting x equal to cos 2 theta. Yes. So I is integral of tan inverse root of 1 minus x upon 1 plus x dx. Put x equals cos 2 theta or 2t, whatever, doesn't make a difference. The derivative will be, take care of that derivative, don't make a mistake over there, cos 2t, the derivative will be minus sine 2t times again 2 dt. This is what you will get, right? Take care of that. And therefore I is equal, I will be equal to tan inverse 1 minus x, 1 minus cos 2t upon 1 plus cos 2t, which is tan square t in the under root, that becomes tan inverse tan t, which is nothing but t. Yes, what I have done is 1 minus cos 2t, 1 plus cos 2t. This is tan square t. Under root of this will be under root of this, which is tan t. And using this, I've written tan inverse. This is tan inverse tan t, which is t. Dx is minus sine 2t dt. And now you can apply by parts on this. Take that minus outside, and then this and this, algebraic and trigonometric, this will be the first function, this will be the second function. That's what you'll have over here. Is there a 2 as well? Yes, there's a 2 as well. Don't forget about that 2. There's a 2 as well. So what you can do is we can take minus 2 outside. Yes. Therefore I will be equal to minus 2 is outside. In the bracket you have first function times integral of sine 2t minus cos 2t upon 2 minus integral of derivative of t is 1 minus cos 2t upon 2 dt is what you get in the bracket. This is what you get. Now integrate that second function. Minus 2 is okay. This is minus t by 2 cos 2t minus of minus plus 1 by 2. The integral of cos 2t will be sine 2t upon 2 plus a constant of integration. So what does this become? Minus 2, this becomes t cos 2t. Minus 2 will be minus 1 by 2 sine 2t plus c. Now we need to replace cos 2t in terms of x. So cos 2t is x. T will be cos inverse x by 2. This minus, what is this? This is 2 sine t cos t. Okay, cos 2t. I can directly replace sine 2t as under root of 1 minus this. 1 minus cos square this plus constant. This is what I seem to be getting. Yes, that is my final answer for this question number 23, as you can see over here. Question number 24 says you integrate this x square plus 1 and the under root, then you have log of x square plus 1, then you have minus 2 log x. Long expressions. Yes, pretty long expressions. How will we handle this? So what I observe is, okay, this is log x square plus 1, this is log x square. Log of something minus log of another something will be log of x upon y form, right? So I will be having log x square plus 1 upon x square. Okay, x square plus 1 upon x square will be 1 plus 1 upon x square. Can I write this also as 1 upon 1 plus 1 upon x square? Yes. So that's the key. I will be equal to integral. Take x square common from here, and this will convert to 1 plus 1 upon x square. This will be log of x square plus 1 minus log of x square in the bracket. In the denominator I have x power 4 and a dx as this. These two logs will club together to give me x square plus 1 upon x square, which is this form only. X upon x power 4 will be 1 upon x power 3 under root of 1 plus 1 upon x square times log of 1 plus 1 upon x square dx. This is what we see over here. Now I can substitute that 1 plus 1 upon x square as t. This becomes log t, this becomes root t, and derivative is with this t. And after that I'll apply by parts. Or to be more pragmatic, what you can do is I can put 1 plus 1 upon x square as t square. How does that help? So this is derivative minus 2 upon x power 3 dx, which is equal to 2t dt. Take care of this. This is 2t. Therefore I will become equal to integral of 1 upon x power 3 dx upon x power 3 is 2t upon minus 2, which is minus t dt. So this becomes minus t dt. What else is there? This is under root of this, which is under root of t square, which is t. Log of this, which is log of t square. Log of t square will be 2 log t. And this is minus 2 integral t square log t dt. Now you can observe there's a logarithmic function, there's an algebraic function. So this will be my first function and this will be my second function. First function and second function. Now I can apply by parts over here. Therefore I will be equal to minus 2 times integral of this will be first function times integral of t square, which is t power 3 upon 3 minus derivative of log t 1 upon t integral of t square, which is t power 3 by 3 dt. This is what you get. Minus 2 remains as it is. This is t power 3 upon 3 log t minus 1 upon 3 t square. The integral of t square is t power 3 upon 3 in the bracket plus constant of integration. and this simplifies to minus 2 by 3 t power 3 log t minus 2 into 1 by 9 will be 2 by 9 t power 3 plus constant. Simply replace t in terms of x after that. So what do I have? T square is 1 upon 1 plus x square. Okay, and I have t power 3 throughout. Oh, we can take out some things common in that case, yes. So what do we have? Yes, we have minus 2 over here and minus 2 by 3 t power 3 can come out common. Yes, yes. And what remains in the bracket is log t minus 2 by 3 if it has gone out. This will be 1 by 3 and t cube has already gone out. This is what you get plus a constant of integration. This is what we seem to get. So what else? The final value will be minus 2 by 3 t power 3 will be this raised to power 1 plus 1 upon x square raised to power 1 by 2 raised to power 3. So this becomes 1 plus 1 upon x square power 3 by 2. Okay. In the bracket you will have log t, which is log of t is under root of this. So under root of 1 plus 1 upon x square, okay, minus 1 by 3 plus constant. Oh, this looks a bit bad. But what I can do is, this is 1 plus 1 upon x square raised to power 1 by 2. That power 1 by 2 will come over here. And maybe I can take this 2 inside. This becomes 1 and this becomes 2 by 3. Yes, that's something which I can do. So this becomes minus 1 by 3, 1 plus 1 upon x square power 3 by 2. And just to make it a bit simpler, this 2 will go inside. This becomes log 1 plus 1 upon x square in the bracket minus 2 by 3 in the bracket plus constant. Take a look at this carefully. I've taken this 2 inside. So this 2 will go in the power. This will become this and 2 will become, this will become minus 2 by 3. Is that okay? Yes. That looks like the final answer with the complete calculations. That's question number 24 for us.